Kinetic of particles, energy methods. In this video, I'm going to talk about the potential energy and conservative forces. Potential energy. The work done on an object by some forces can be expressed as a change of a function of the object's position called the potential energy. dV is equal negative F dot dr. F is said to be conservative and V is called the potential energy associated with F. When all the forces that do work on a system have this property, we can state the principle of work and energy as a conservation law. What is conservation law or conservation of energy? If all of the forces that do work on an object are conservative, the sum of the kinetic energy and the total potential energy is the same at any two positions. For example, if the kinetic energy increases as the objects move from position 1 to position 2, the function V or potential energy must decrease, and vice versa. So the work done by conservative force is independent of the object's path. For example, if objects move along a closed path and returning to position 1, the work done by a conservative force is 0. Let's look at some application of potential energy and conservative forces. In figure 1, the potential energy stored at the top of the roller coaster is transferred to kinetic energy as the car descends. In figure 2, the elastic potential energy stored in the trampoline is transferred to kinetic energy and gravitational potential energy as the girl flies upward. We can apply conservation of energy only if the force doing work on an object or system are conservative and we know or can determine their potential energy. Look at object A. If the weight is the only force applied to this object and object A moves from y1 to y2, the potential energy of the body with respect to force of gravity is equal W times y2 minus y1. I choose position 1 as a datum. Choice of datum from which the elevation y is measured is arbitrary. As you can see, the work is independent of the path followed and it depends only on the initial and final value of the W times Y. And unit of work and potential energy are the same, Newton meter or Joule. Work of the force exerted by a spring depends only on the initial and final deflection of the spring. The potential energy of the body with respect to the elastic force, we show by VE, is equal 1/2 k times x squared. Note that the preceding expression for VE is valid only if the deflection of the spring is measured from its undeformed position. Non-conservative forces. Until now, we talk about conservative force like weight and springs. Now I'm going to talk about the non-conservative forces. In non-conservative forces, the work is proportional to the length of the object's path, and therefore is not independent of the path. For example, friction force are not conservative. Suppose that a book of mass m rests on a table and you push it horizontally, so it slides along a path of length L. The magnitude of the force of friction is mu times W, and the direction of the force is opposite to that of the book's motion. So the work done by friction force is negative mu times m times GL and depends on the path. When both conservative and non-conservative forces do work on an object, the principle of work and energy can be expressed in terms of potential energy as a conservative forces and work done by non-conservative forces. For potential energy, we show by V, and for non-conservative force, we show by U. Let's look at some examples. A 20-pound collar slides without friction along a vertical rod as shown. The spring attached to the collar has an undeflected length of 4 inches and a constant of 3 pounds per inch. If the collar is released from rest at position 1, determine its velocity after it has moved 6 inches to position 2. First, we must confirm that the forces that do work by collar are conservative. Apply the principle of conservation of energy between position 1 and position 2. The problem is given the collar slides without friction along a vertical rod. So the work is done only the weight of collar and the force exerted by the spring. And the system is conservative. Okay. Now we have to apply the principle of conservation of energy between position 1 and position 2. First, we have to define your datum. I choose position 1 as a datum. Okay. We have to write the elastic and gravitational potential energy at position 1, and as you can see, the initial kinetic energy at position 1 is 0. But for potential energy, we find VE 24 inch, and for gravitational force is 0 because our datum in position 1. In position 2, the potential energy or elastic for a spring is 54 inch-pound. For gravity is negative 120 inch-pound. And for the kinetic energy, we have to find the velocity. So when we apply the conservation of energy, we can find the velocity at point 2. The velocity is 4.91 feet per second, and the direction is downward. Next example. A section of track, a roller coaster, consists of 2 circular arcs AB and CD, joined by a straight portion BC. The radius of CD is 240 feet. The car and its occupant of total weight 560 pounds reach point A with practically no velocity and then drop freely along the track. Determine the normal force exerted by the track on the car at point D. Neglect air resistance and rolling resistance. This problem has a two-part. You will need to find the velocity of the car by using the work and energy, and then use Newton's second law to find the normal force. First, draw a diagram with the car at point A and D and define our data. Now, we use the conservation of energy to solve VD. Okay. We have to find the gravitational potential energy at point 1 and 2. As you can see at point 1, the kinetic energy is 0, but for potential, gravitational potential energy is 84,000 foot-pounds. At point D, the velocity, we have to find it, and the gravitational potential energy is 0. After we solve this by using the conservation of energy, we can find the VD. The VD, the velocity at point D, is 98.285 feet per second. We have already found the velocity at point D. Now we draw the free body diagram and kinetic energy of the car at point D and determine the normal force exerted by the car on exerted by the track on the car by using Newton's second law. The summation of the force in the normal direction equal mass times acceleration in normal direction. And instead of an, we can write the v squared over rho. But we have a circular motion, so the rho equal r. The r is 240 feet. Now, the normal force is 1,260 pounds. Thank you for watching.